Welcome back, everybody. In this video, we're going to get familiar with machine learning so you can see how reinforcement learning fits into the picture. It's 2028 and Neo has just purchased his new CoffeeBot 5000. It's an artificially intelligent robot designed with a singular purpose, to fetch coffee for its caffeine-addicted owner, Neo. Neo fancies himself a machine for turning coffee into code so he can justify the purchase with the increased productivity. CoffeeBot 5000 is highly advanced. It's comprised of multiple AI systems working in tandem. It's got high-fidelity vision with object recognition capabilities, speech recognition in 50 different languages, and is programmed to learn the habits of its owner to better serve them hot coffee on demand. On the very first day, Neo asks CoffeeBot to bring him his morning cup. He sets up his work for the day and hears a yelp out of the kitchen. He bolts in to see what happened and sees his puppy looking terrified. Apparently, CoffeeBot stepped on the puppy's tail without so much as a second thought. The puppy is okay, but Neo is shaken. How can he trust the CoffeeBot to not obliterate his pet on the way to getting coffee? Why would CoffeeBot be so sadistic? In this lesson, I'm going to answer the question of why CoffeeBot seems antisocial. As we will see, it's not really. Rather, it's operating at the limits of its capabilities. To see this, we're going to take a few minutes to get a brief overview of the current state of machine learning. This is important so you can understand where reinforcement learning fits into the picture and why it's so critical to advancing the field of artificial intelligence. In general, machine learning algorithms fall into two major categories: supervised and unsupervised learning algorithms. Supervised learning is typically used for classifying objects into groups, and it is great for tasks where we know the ground truth label of the thing we're trying to classify. This is what makes it supervised. It's similar to a course instructor correcting the student when they make a mistake. Unsupervised learning is used when we don't know the ground truth labels of the things we're trying to classify. It works by finding commonalities in the data and grouping them together based on their distance from some point in parameter space. In contrast, in supervised learning, we are making predictions on what class a data point belongs to based on the previously seen training data. When the algorithm gets this prediction wrong, it is assigned a penalty or a cost. The algorithm seeks to minimize this cost. In both cases, we're trying to optimize the parameters of the model to either reduce the distance between points in a group or to reduce some cost function associated with our predictions. While they are similar in many respects, the tasks they are best suited for are quite different. Supervised learning is particularly well suited for tasks like image recognition. This can include static images such as pictures, or moving images from a camera like what you'd find in self-driving vehicles. For example, if we had 500 images of dogs and 500 images of cats, we could feed these into a supervised learning algorithm to teach the system the differences between the two. It's worth noting that we're not limited to just two classes. We can make the algorithm work for any number of classes so long as we have enough training data for each class. Classifying data based on labeled training data is what is called logistic regression. So how does the algorithm learn the differences between the classes? We can start by inputting our training data, also called model features. For image recognition, this is the raw pixel data of our set of images. For each of these features, our input pixels will have some weight which we initialize randomly. These weights just tell us the importance of each pixel in classifying the image. We can then use the features and weights to get some set of predictions for our images. These predictions are compared to the training labels, which are just the actual classes the input data belongs to. Since our weights were initialized randomly, they're going to produce the wrong predictions and give us a large cost function. The algorithm then systematically changes the model parameters and sees how this affects the cost function for each image in our training set. What we're doing here is getting the dependence of the cost function on the weights, and the algorithm will change the weights in such a way as to minimize the cost function. This process is repeated for some set number of times or until it converges to some really low cost that gives us a confidence that the model is good. Once a model is trained, we can test it with new images to see how it does. Sometimes the model will fit the training data really well, but won't do well on the test data. In other words, it can fail to generalize. It's important to note that this isn't limited to discrete classification. You can also use supervised learning to predict continuous variables. For example, we can use supervised learning to predict loan default risk. Given some information about the borrower's credit history, income, demographics, and many other factors, we can predict the probability of loan default. This is called linear regression, and the algorithm is identical to the image classification example you just saw. In unsupervised learning, we are trying to group points together to minimize their distance from some central point in parameter space. For example, let's say we're trying to group together visitors to our e-commerce store to better understand their demographics. The end goal here is to better tailor our content and marketing to improve sales. We collect a bunch of parameters from Google Analytics and the Facebook Pixel and then input them into our model. These form our parameters, and they would include things like demographics and interests. When you visualize the points in parameter space, they might look something like this. To cluster them, you pick 2 random points in parameter space to be the central points of the distributions. Then assign each data point, which corresponds to a visitor, to the group whose center is closest. Then you recalculate the new center of that distribution and reassign points to their closest center. Just repeat until you no longer need to reassign any data points. This will help you see strong correlations between parameters that can tell you exactly who visits your store so that you can better tailor your content. This is called the k-means clustering algorithm. In this case, we used k equals 2, but you can use any number of groups depending on either knowledge of the training data or trial and error. We can also use unsupervised learning to identify anomalous data points. Here we take a large distribution of points and see if our new data point is far outside the distribution. A classic example would be credit card fraud detection. Most people's spending habits are fairly routine. Weekly grocery trips, gassing up their cars, and paying other bills are all fairly normal occurrences. If a new purchase in a strange location pops up, the credit card company can be flagged because this is outside the normal distribution, and they can then place a hold on the account. This has probably happened to you, and usually it happens when you're out of town on vacation, just the perfect time to be cut off from credit. By now, you may be able to see the limitations of these sorts of algorithms. They all rely on pre-existing data to classify new data. While this works very well in controlled environments, there can be some significant room for error when presented with new data that is so dissimilar from previous examples that the algorithm completely falls apart. In other words, supervised and unsupervised machine learning algorithms have very narrow use cases. They may be great at one specific task, but they don't generalize. Worse yet, they don't really mimic how biological systems learn. You don't have to see thousands of images of dogs to know what a dog is. You probably only saw 1 or 2 dogs and you got the idea. Another limitation we run into is the fact that these algorithms require large amounts of data. This makes generalization especially hard, as we can't possibly provide data for each and every contingency. Finally, they lack a model of the world in which they operate. They're just pattern matching algorithms. They're not really intelligent in any meaningful sense of the word. So, turning our attention back to the coffee bot, we can explain the aberrant behavior. The coffee bot is just a collection of algorithms that are attempting to minimize some abstract cost function that doesn't closely correlate to what humans value in the real world. We could correct the behavior by programming in exceptions to the walking algorithm so that it doesn't step on our puppy, but could we realistically anticipate all the variables in the real world? It's highly unlikely. The vision and speech recognition systems are very narrow AI. They are limited to a very specific function. While they can perform that function spectacularly well, they aren't really intelligent. But not all hope is lost. Reinforcement learning has emerged as a path towards more generalized artificial intelligence. The basic idea is that instead of trying to minimize cost functions, we're trying to maximize a reward. We can structure the reward in such a way as to minimize the potential for unwanted behavior and to get a more generalizable type of intelligence. Of course, it's not perfect, but it's our best route forward. That's it for this video. I just wanted to give you a really high-level overview of what constitutes machine learning so that we can see where reinforcement learning fits in. In the next video, we'll get our first introduction to reinforcement learning.